All right, let's go ahead and start today. This week, as I've been saying, it's going to be very important. We will still cover quite a lot of stuff that is related to MDPs, Markov decision processes, because reinforcement learning in its core is actually solving an MDP. But how we get to the MDP is very different from what we covered from in last week. Okay, so today, very interesting, with a lot of exciting real world applications that we are actually going to take a look at partly from today, and then we will be coding, programming, like basically I will be doing that to solve some of the problems using reinforcement learning. That will include robotics, video games, et cetera, okay? Solving some real world problems. So we will look at the, various advanced developments in AI, especially based on reinforcement learning, okay? So we will look at the basics. We will also cover quite a bit of MDPs once again, because that is basically the foundation building block of the reinforcement learning. And we will look at both model-based and model-free learning. We will talk about what model-based is and what model-free learning. With model-based learning, it will look very similar to MDPs, where we do have transition matrices and also the reward functions, where we basically assume that we know how the world works. But in most of the real world problems, we basically don't have any transition matrix. We don't have a reward function. We don't know how the world really works. It's uncertain, as what we've been talking about, right? And then we're going to talk about Q learning, how to basically learn the best action to choose in a certain state that you are, and several variations of Q learnings, such as the basics, the temporal difference learning in SARSA. So we will talk about SARSA. This is simply just a shorthand of state, action, reward, and next state and next action. Okay, so SARSA, we actually have been talking about Expectamax, okay, how basically you transition from one state to another by choosing a certain action. Okay, so we'll talk about something like this quite a bit this week, and probably, I think, partially next week too, because I think I've realized that the number of applications that I have prepared and the programming and the coding that we will have to go over, I don't think only the next lecture will be enough for reinforcement learning. It will be very unfair to just spend only 1 week on reinforcement learning. One thing I also have to mention that reinforcement learning in itself is an entire course in majority of the well-known famous campuses around the country. So we will try to at least cover the basics of it, and then we will try to cover several applications or several real-world problems that are solved using reinforcement learning, such as robotics, self-driving cars, etc. So a very simple workflow of reinforcement learning is that you have an agent, all right, that perceives the environment, okay, sees what the environment is, takes a certain action, okay, and then basically gets a certain reward based on what the result from the environment is, okay? So the agent basically takes an action, right? Then the environment plays its part, the Expectamax part, which is why this is the kind of a circular, not the circular, but this is the green one. That is the Expectamax. That is the result of your action, right? So the agent basically takes an action. The environment plays its role. That's the result of the action of the agent. And then the agent basically gets a reward and gets into a next intended state, okay? So in short, although reinforcement learning looks very simple, extremely simple, where we have an agent, and then basically it interacts with the environment, gets a reward, and then maximize basically the expected rewards. Remember the short living rewards and then the final reward. So the idea is to still maximize the sum of rewards that we have, how to come up or shape the policy which we are going to follow in order to maximize our rewards. So although it looks very, very simple, but solving real world problems using reinforcement learning MDPs is extremely difficult, very, very hard. And we will talk about that in this week, okay? And we will see several problems, how it can get really complicated. But the idea basically is kind of the same. the agent basically takes an action, gets a reward, or gets a feedback. That's the result of the action. The environment plays its part. And then the agent's utility, the reward, feedback, and the utility are exactly the same what we have done last week, MDPs. Okay, so very similar, the first two part, and then the agent is required to learn or act in the environment to maximize its expected rewards. And the learning, basically how it is different from MDP, the learning is based on observed samples. What we do is we let the agent interact with the environment and then learn how to get these rewards by interacting with the environment instead of sitting and thinking and planning, just like how we have been doing in the past 5 weeks in the search, mostly search problems. Now, what we do is we let the agent just go interact with the environment, pick up the samples, observe what it has been observing in the environment in an uncertain environment, note down the rewards, and then shape up the policy, shape up the strategy that it has over time based on the observed samples that we have. So that's the major difference between the reinforcement learning and the MDP. So let's go with just a few examples, very basic examples. This was the robot that was actually done at the University of Texas at Austin in 2004 by Peter Stone's lab. Basically, they designed a robot and then used reinforcement learning to train this robot on how to walk and how to get to a destination using a certain policy, certain strategy that the robot will use over time to learn how to walk or to get to the destination as fast as possible. Okay, so the idea behind the robot is basically, one very simple way to program this robot is simply just write down the movement function, right? So you have the servo motors, right? All the motors in its legs and arms, and it has a camera that is mounted on its head, right? So what you can do is you can simply write down a movement function. Like, okay, if you move left arm, then the right leg moves, and then right arm, and then left leg moves. And if you keep, using those sequences, you can basically make the robot walk, right? But in reality, in uncertain environments, it's not going to work really well because it's going to have obstacles. It will need to have movements and turn left, right. So in an uncertain environment, it's not going to work that well. So what we do is the job of the reinforcement learning is to find out basically the best sequences of actions to take or how to move those motors basically by interacting with the environment and then come up with the best policy that gives us the best reward. And the best reward in this case was actually how to make the robot move, walk, or even run as fast as possible to the destination. Okay, so basically you see in the initial phases of training, what you do is the robot basically is this is the basic policy. Basic policy of this robot was to just move forward. Take some, sequences of actions to just move forward and follow a pattern. You see those lines? So the idea was to make the robot move with the basic policy, very basic policy. So very basic policy was to always move forward, right? So initially, basically, it's just moving in a random, like in a random sequence. The movement is not that great. After, a little bit of training, that it gets better, much better at actually following a path because your policy, after the robot basically gets the rewards, after several iterations, several episodes, it shapes up that policy. Remember in the policy in the map that we had last week, that there are value functions for each of the cell. If you take a look at the grid world, right? And then there were arrows, like from this cell, from this actual cell or square, where you should go next as an agent. So it is shaping up the policy after being trained, and once it is finished training, it basically becomes a really good walking robot, like an Olympic level walking robot that goes to its destination really well. Now, one policy for this robot is basically to always just move forward, right? Just move forward. But imagine if you are designing a robot that actually also plays soccer in a field, right? So if this robot is moving in a random direction or there is other uncertainty that is involved, such as, like, let's say there's an earthquake, right? So it also has to look at the very clear view. Suppose that you're designing a soccer robot, and it also has to have a constant, track of where the ball goes, right? So that means your computer vision or your video processing also has to be really stable. So then you can add more complexity in your robots instead of just walking forward, but you can also see that your video has to be really stable in order for the robot to play really optimally well in the environment, right? So there can be multiple factors that can be added that can be added to make the reinforcement learning or the policy, the shaping of the policy much more complicated than just normal. Okay, so these are the factors that can play in a real world environment, but the best part about reinforcement learning is it actually finds out those sequences of actions and makes the trade-offs between the stability of the factors that you have and then the uncertainty that you have, and then it basically shapes up the policy in iterations. So there's another robot is basically running cheetah. That was what I think initially started with Google, and then there have been several different variations of running cheetah. So basically, initially, what you do is you start this simulation. By the way, this is just the environment that was created. So it's not actually in a real world environment, but there is a Python environment that was created in order for the cheetah basically to be able to get up, start walking, and then start running as fast as possible in any direction, not only just forward, right? Okay, in any direction it should start running. So initially, if you see that, okay, this cheetah can be in real world. Okay, cheetah robot can have few motors here, few motors here, right? Few motors here, and it may have a video camera that is mounted on top of here. So that can be a real world cheetah. So initially, you see, without any training, it has no idea what it is doing because it is given a given policy. Based on the given policy, is trying to make a few actions in order to be able to run, to see, or be able to walk and learn in the environment. But after several iterations, the reinforcement learning plays its part and tells it how to move the motors to be able to walk and run fastest. And eventually, it will basically become actually the fastest animal by running really fast. After several different iterations, the return increases because the policy is being shaped up, and now your return reward keeps increasing because it is learning what are the best actions that it has to take in order to maximize its sum of rewards. Okay, so eventually it will become a really fast, running cheetah. There was, I think, several years ago, at least 4 or 5 years ago, Google basically trained a robot that did not know how to get up, stand, walk, and run. And they designed the walking or running robot based on reinforcement learning. Okay, so eventually you see its score keeps getting increased. Sorry? Oh, sometimes it decreases because you see, even if you make a robot, sometimes the robot will, or your agent will make moves that is trying to follow the policy that is intended to, but the environment doesn't play the role the way you have the intended. That's where the uncertainty basically lies in. So sometimes you're trying to take the actions that should give you the maximum reward, but because of the return or the feedback or the result from the environment, it is not as intended as it is not as good as you intended. So that's just one episode, right? Based on different episodes, you may find out that there might be higher rewards sometimes, there might be lower rewards sometimes. So you have to look at the samples by interacting with the real world environment and by having multiple thousands and thousands of different samples or hundreds of different samples to find out what are the best actions to take, even when there were some lower rewards sometimes. Okay, so we average those, and we basically implement several algorithms to learn, basically to learn the policy or shape up the policy. This is another robot that was it's called the toddler robot that was done by some very difficult names, but in 2005 from MIT. Nathan.
So with reinforcement learning, they're honing the what do we call it? So we're still providing the reward.
Uh, the reward function is being provided, but our job is going to be able to learn the immediate rewards that we get. Because in MDP, we saw that we actually do have the transition function. We do have the immediate reward functions, immediate rewards. All what we have is we now have the final reward, the major reward that you have. Just like training your dog how to how to jump, and then just give it a cookie, right? So that's the final reward. And then in the intermediate steps, it will have to learn how to basically jump higher and higher to get higher reward. So the reward and the probability and the way to take the actions is going to be the reinforcement learning's job. How to take the actions. That's what we're going to cover today, and basically in this entire week. So in MIT, what they did was they trained this toddler robot how to walk, how to walk forward. So this is kind of a very interesting robot, because now the policy that it is given is actually how to walk forward, right? How to take some steps, right, and walk forward. But it's not just only walking forward, because there is hardware involved in it too. So the hardware, the uncertainty in the hardware also has to play a role for the reinforcement learning to shape its policy. Okay, so in the beginning, the toddler basically learns how to take a step, and then its job is to move forward. And then after several iterations, it will start moving around in the room, and then start making, just like a toddler, making random moves. And then after that, basically being able to learn, it's eventually moving, and now it's actually moving in the in the building after learning several minutes of training. And at the end, at night, it's just off to college. It's just going home now. Okay, so it was a very interesting robot that was done at MIT back in 2005, 17 years ago, which was pretty interesting. Okay, so yeah, there's a foam that is installed so that if it falls on its right or left, it is safe. It doesn't. Yeah, they should save it, but that's what I should say the cost involved in reinforcement learning is much higher than the cost that when you do just simple MDP or in the environment where what the environment is. So we will see, we actually let the robots go in the environment, learn, interact with the environment. And in that case, reinforcement learning actually, makes you waste a lot of computational resources, waste a lot of hardware too. You can, you destroy quite a lot of robots. And we will see several examples of how this can be destroyed. Now let's talk about the difference between, the MDP and reinforcement learning, and that's where basically the things that are unknown that play the part. So the major, so there's quite a lot of similarity between MDP and reinforcement learning. Okay, we still have the set of states, we still have the set of actions. So it's not only just about robots, by the way. Reinforcement learning is not only just about the robots. You can solve any real world problem that can be transformed into an MDP. All right. So we talked about the car racing, right? Basically, there are a set of states that are available for a racing car. There are a set of actions that you can take. Something like this. This was like, if you are, driving fast, then there's a 50% chance that your car will remain cool, and then you will get a reward of +1. And then there's a 50% chance that it will get warm, and it will get a reward of 2, et cetera, et cetera. So we had basically a model, right? A model of the world, or the transition matrix, right? What happens if you get transformed from one state to another, right? So we had all those transition functions, all those transition probabilities, right? And we had the transition matrix. That's the model of the world, right? We say that if the car moves at a certain speed, slow, or fast, there's a 50% chance that you will get into another state and get such kind of a reward. And then there's a 50% chance that you will get into a warm state and with a certain reward. So we had all the reward function and the transition matrix. We are still looking for a policy by doing, remember, value iteration, right? Policy evaluation, policy extraction, et cetera, right? Based on the transition matrix. and the reward function that we had, right? In reinforcement learning, we really don't have TNR. Basically, it's not that we don't have TNR. There is a transition matrix, okay? There are probabilities that exist. We simply don't know them yet because we haven't interacted as an agent, we haven't interacted with the environment, and we really don't know what's going to happen, what is going to be the output or outcome if we take a certain action in the world. So what we do is we learn along the way. We take several different iterations or several times, several episodes of learning. Basically, in reinforcement learning, we really don't have any of this. Okay, that's what we have to learn about. So actually, there is no knowledge of good states and what the actions do. That's what we have to learn in reinforcement learning. Okay, try out different actions and states to learn. And how that can be done, there are a few ways, basically, to go through that process. So, a very basic difference that you can always remember, a simple difference is that MTP is offline learning, while reinforcement learning is online learning. What do we actually mean? In the grid world, remember that we had the value, right? Where there was one state there, when you get to that state, you can take an exit and get the bigger reward, +1, right? And then there was a -0.03, -0.4 immediate reward for taking actions, right? Or moving squares in the grid world. But actually, what you were doing was you're not interacting the real world environment. You're just sitting and you're thinking, you're planning. It actually is happening in your head. As a robot, you say that, okay, I'm in a certain state, in a certain square. What happens if I take left? Okay, and then by looking at the value, value function, we say that if I take left, I'm going to fall into the fire pit. I'm going to fall into the pit. So I'm only planning. In real world, in reality, I'm not doing anything. I'm just planning. It's going on in my head. That's offline planning. That's offline, MTP. Reinforcement learning, what you do is when your robot is in a certain, or your agent is in a certain square, it says, what happens if I take left? Well, I don't know. Let's try it. It just goes in the fire pit. It learns that it was basically, not the best function or not the best move to make, right? So that's why in reinforcement learning, you lose quite a lot of robots, quite a lot of hardware. That happens because you let the agents interact with the environment. And then it also depends on how quickly you adapt. You say that last time when I took a left from this state, I got destroyed. So this time I shouldn't do it. So it also depends on how quickly you let the robot agent. And that's the concept called exploration versus the exploitation. So towards the end of this lecture, we'll talk about what's the trade-off between the exploration and exploitation. Okay. All right. Model-based learning, model-based reinforcement learning. What we do is we still basically have an uncertain environment. The environment is unknown, but based on our domain knowledge, we construct a model. We construct a model of the environment. We imagine or we think that, okay, this is the world might look like for our agent. If we are letting it move in a certain environment, in a certain room, our environment might look like this. So what do I even mean by constructing the model? Basically getting the T and R, right? Transition matrix and reward function. That is our model. Because once we create the model of the environment, we really then know what the T and R is. Okay, so we construct a model, we estimate. Okay, we estimate, we get the best estimate of the environment that we have to interact in, and then we get those functions, get those values, and we utilize those in order to solve an MTP. Okay, something like this. Okay, so model-based, learn an approximate model based on the experience that you have. All right, and then solve for the values. And solve for the values, what do I mean by solve for the values? Basically either use value equation or policy evaluation, just as before, as last week that we have. How do we construct the model, or how do we learn the empirical model, MTP model? Empirical meaning, so you see, count the outcomes. So number of times in a certain state, you took a certain action and you went into a next state. Okay, that might be always intended, or that might not always be the state that you are, that you got in is as an intended state. So you take all that experience, all those samples, and then simply normalize. T hat is like just an average. Okay, you just learn the transition matrix, which is S, A, and S prime, right? You're in a current state, you took a certain action, and you get into a next state. And then you just create that matrix. Okay, so you basically learn that by simply averaging, simply taking the average of a number of different multiple times or iterations, number of different episodes or samples, and then you get that. And also, every time you take an action, you got a reward, and you simply note it down, right? As a robot or as an agent, you simply write it down, and after collecting several samples, you simply average those, right? Get an average of those, which is why I'm using R hat and T hat, right? When we experience. So we get those, and then we simply, plug those values in, and we really solve for MDP. Then it really becomes an MDP, right? Just an example, something like this. Suppose that you have this really, really simple grid world, 3x3 grid, all right? And you have the policy. You see here? So the arrows basically indicate. So I don't know why I don't have the letters. Okay, this is A, C, and this one is B, all right? So what we do is we are given an initial basic policy, a fixed policy that you see here, these arrows. So we are given this policy, a fixed policy. We take several samples, right? We observe, and then we come up with the T and R. How can we do that? Something like this. You see, in the first episode, we were in B. Okay, we are standing in the square B. From B, we take east to C, and we get a reward of -1. And then from C, we take east to D, and we get a reward of -1. And then from D, we exit, and we get a reward of +10, right? And then in the episode, in second episode, we do again the same thing, right? Suppose that we do again the same thing. And next time, in the third episode, let's say we put the agent in state E now. And then what happens from the state E? Okay, then what happens from the state E? All right, from E, we take north, we go to C, get a reward of -1. This is the short living reward of -1. And when we take the exit, we get the larger, bigger reward. Okay, and then from C, we go to east, we take -1, and then from D, we exit. And here, from E, we take north, we go to C, get reward of -1. From here, we take east from C, but the environment puts us in A instead of instead of D. Okay, so that's where the uncertainty is. So we take multiple samples, right? And then we calculate or we estimate the T hat and R hat. Where does this number come from, by the way? The probability. So the transition from B to C by taking an action east is 100%. Look at all those samples. Look at the first 2 episodes. Look at all the samples and see where B from taking action east from B to C, what happens? Yeah, because of the fixed policy. See, every time we are in B, state A, right, and state S, and we take an action east, we end up in C, in this and in this episode, right? Every single time we took an action east from B, we landed in C. We landed in C, right? So that means that whenever we are in B, we're taking an action east, we're always going to end up being in C. That's why it's the 100% probability. So we calculate those probabilities, and then we come up with a reward function. Okay? Are these rewards correct? Who knows? We don't know yet. So the optimization of reward function is also another, problem to solve in reinforcement learning. We'll take a look at that in a few minutes. Okay, so we get the reward function. Here is another, learning to fly. Now you see what we have is what was that? So I just put this robot. Now that is also a very interesting robot, basically a drone to teach a drone how to fly. And the reward, the highest reward is the longest flight time, longest flight time. In the first basically few, training samples is just trying to learn how to fix those, the motors that you have in order for it to be able to learn how to fly for the longest amount of time. Okay, so flight time, like 2 times slow down. So after, I think, several iterations, it actually learns how to, like fly and increase the flight time. So as soon as it learns, slowly starts to learn how to, maximize the reward, it basically learn how to stay in the, in the air for the longest possible amount of time. So it was, I think, 6 seconds or something. So that's another, way to use reinforcement learning to, to maximize the expected rewards. All right. So we talked about model-based learning, right? We construct a model. How do we construct that model? How do we know that averaging is going to work? Okay. Now, with a very simple example, let's just, go over the example of the class and compute basically the expected age of CSE, this class, the students of this class. Now, suppose that, by knowing all of you, I know the probability distribution. I know who is at, of what age. So I actually have the probability distribution. Like how many people are in the class who are aged 20? How many people who, are 21 years old? How many people who are 22 years old, et cetera, et cetera. So I know the probability distribution. All what I do is I just get the weighted average, right? Just like Expectamax, right? We just multiply the number, all possible numbers, let's say from the age of 20 to 50 or 60, right? And we multiply that number by the probability from the distribution that I have, right? And then I simply get the average. Something like this, that there's a 35%, chance that a randomly picked student in the class is the age of 20, right? And then we just, simply get the average. That's model based, okay? What happens when we don't have a model? What happens when we don't have the probability distribution? Okay, what happens then? Well, another simple way is to just collect samples. Like I'm gonna ask Ronald, how old are you? Then I'll note it down. I'm gonna ask Sophia, I'm gonna ask Nathan, right? I'm gonna ask multiple people and then note down their, their age, and then construct a probability distribution. Then come up with a probability distribution after collecting several samples, right? A model-based approach is basically to get those students who I asked their age for, and then simply divide them by n, by total number of students, right? And we get the average, or we get the probability distribution. And then we plug that in into the equation at the top, and we simply get the, probability, right? Another way is to just simply average, right? I have the age of, let's say, all the students. I get their age, divide them by the total number of students. That also works. What's the difference between this one, model free, and model based, and why they both work? Okay, so eventually in model based, eventually when I basically get the samples, know the age of the people, and I can eventually the probability distribution will get correct, because the more I know the age of the students, more students, the better the probability distribution will be, right? So that definitely works. How about if I just simply take the age of every student and just simply divide them by n? Now here, I'm getting the probability distribution. Let's say the probability of a student with age, let's say 20, 21, will be much higher than the probability of a student who is age 60 in this class, right? Here, I'm not doing that. I'm not multiplying the probability. And why does this still work? Why does this simple average still work? Why am I not putting more weight to the student who is 20 years old, as opposed to putting, much less weight to a student who is 60 years old? Anyone? Any idea? Why does this still work? Why does this average still work? is your actual environment. And so you see, we implicitly, I'm getting the age of all the students, right? We implicitly, the frequencies of every single age appear higher. So there's an implicit, embedding of basically putting more weight, because if there is a student, if there are more students who are 20 years old, they will be in the sum here. That's why this average works too, because the samples appear with the right frequencies. That's why they both work. So we're going to talk about model-based reinforcement learning, having the probability distribution. That's what we did. Just what we did, right? We took a sample. We took multiple samples, and then we came up with the t hat and r hat, right? And there are, other parts where we really don't know the probability, and it's a model free too. There are some instances where we can't construct the model. That's what mostly uncertain environments, real world environments are. Yeah, that's, you really don't know the model of your class, right? So that's when you really don't have any information about the model. You cannot really construct the model. From there, you will have to basically use a model-free learning. And we will also, see what's the distinction between model-based and model-free. In model-based, we really construct the model from the assumption that we know the environment. In model-free, we really don't know the environment. And we have to construct, or we have to simply update our estimates as we go along. Okay. So in model-free, as we just said, that we just simply directly take the average, direct evaluation. That's called the direct evaluation. Or, directly average the sum of rewards rather than learning transitions and rewards. So we really don't have the T and R functions in reinforcement learning. In model-free, there does exist T and R, but we simply don't know that. And we don't know it until we interact with the environment enough number of times to come up with the averages, to get the direct average, right? Right? How can I calculate the average of this class when I haven't even met anyone? So I will interact with everyone, in the class. And then after that, after learning a little bit, taking samples, observing the ages of different people. And then after that, I'll be able to get the direct average, right? So that's actually called the passive reinforcement learning. So the simplified task is still to do evaluate the policy. Initially, you're given with a fixed policy, right? And you really don't know the T and R. And the goal is to learn the state values. In this case, what we do is we let the agent, or we let the robot interact with the environment. Every single step it takes, it notes down the immediate reward that it had, and what happened when it took a certain action from a certain state. So it's basically the learner is along for the ride. So there's no choice about what actions to take. There's no choice given. It just simply observes the environment, learns, takes a note of it, everything what it has done, and simply calculates the average, directly calculates the average from its direct interactions. Okay, so that's the passive reinforcement learning. And that's also not offline, by the way, because we are still letting the agent interact with the environment, right? One by one, several episodes, several steps, and then improving the average as it goes along, by taking different steps in the environment. All right, so the goal basically is to compute the values. Remember, in the grid world, we really had the values for each of the square, right? So we propagate the value back, and we simply get the values, right, for each square. And we simply also get the immediate rewards. We also get the Q values. The Q values is what action to take. In the grid world, it was just simply 4 actions, right? North, east, south, west. And then each action had a specific value assigned to it. So remember, in MDP, we covered in last week was that get a state value function, state value, and get also Q value function to learn Q value. So we'll first start with the state value functions. We have to learn, like, what is the reward from moving from one square or from one state to another state. So we will get the values first, okay? So what we do is every time you visit a state, according to a fixed policy, every time you visit a state, write down what the sum of the discounted rewards turned out to be, average those, and update your policy. All right, just like for the robot, initially it had, it didn't have a really good sequence of actions, even though it was trying to follow a specific policy. But after several iterations, it actually learned where the maximum reward is, where the best reward is, right? And then it updated the policy, right? So this is called direct evaluation in passive learning environment. Let's just take a look at the direct evaluation of the value functions. Remember, we're calculating the state value function in here, okay? Let's see how we do that. All right, now assume that gamma is 1. The learning rate basically, is or how far-sighted you are. So an example of, state value function is something like this. We get the episodes, right? Episode 1, just the same. Okay, episode 3, episode 4. And then we simply evaluate, or we get the rewards, okay, from every single state that we visit. We write that down, the rewards, and then we simply calculate the value of the state that we just left. How do we do that? Let's just try to use the formula that we had. Something like this, okay? So where did this 8 come from? You see, in these episodes, I left B, I went to C, I got a reward of -1. I left B, basically, and then I left C, and I went to D by taking east. I got the reward of -1, and then finally we took the exit, and we get the reward of +10, and we get the value of +8. So we evaluate and we get the direct average from different episodes, from multiple episodes. There's a problem with direct evaluation. There's a really serious problem with direct evaluation. First of all, well, the good thing about direct evaluation is it is very easy to understand. It doesn't require any knowledge of TNR. Okay? It doesn't require any knowledge of TNR. Once again, those rewards of -1 and +10, who knows this is correct? We're not sure yet. We don't know. Where do those rewards come from? We'll talk about that in just a few minutes. Okay? So it eventually computes the correct averages. But what's bad about it? It actually wastes a lot of information. From every single episode, you actually calculate the value. You calculate the value. And now there is another problem with, with the direct evaluation is, if you look at this policy and if you look at the values. Now you see, going to C from B and from E, right? And from E. It is actually the same if you look at this. You see, from E, you take north, you go to C, and you have the same reward of -1. Okay? From E, you take north, go to C, and you take a reward of -1. That is the same as going from, from B to C, right? From B to C. You also take the same road. But how come B is +8 and E is only -2? It's because you look at this episode. You took, E from E to C by taking north action, took a reward of -1. From C to East A, but you landed in A. And then from A, you took the exit and you got the worst reward in here. That's why, first of all, it takes a lot of computation to calculate the values, right? Recursive function. Plus, it has no connection among the states. There's no connection, right? Going from B to C and E to C looks the same, but their values are very different. So there's no, connection among the states. Yeah, so that's the problem with the direct evaluation. We have to fix that, right? We have to fix that. Why don't we just do the policy evaluation? Why don't we compute the values, all right, by looking at one step ahead? Just remember, we did the policy evaluation by looking at one step ahead and then see what happens. By looking at one step in the future and then finding out the values, by taking a certain action. What happens then? All right, something like this. We have the fixed policy pi s, right? From a state, we have the expect max nodes. Remember, Because if we take an action, we're not sure that we're going to get into an S prime. We might end up in S1 prime, S2 prime, S3 prime, or Sn prime, right? So that's why we are using the expect max. So what we do is we just have still apply Bellman equation, all right? We recursively apply Bellman equation, and then we calculate the V for a fixed policy. But we simply, at each round, we replace the V with a one-step look ahead layer over V. How do we do that? Let's go over this. So initially, V pi of 0, and we apply this function. Remember, we still have our transition. Basically, that's the transition from one state to another. That's the reward that we're getting, right, from one state by following a certain policy and landing into another state, and the value of the future state. All right, we simply, and then this is the discounting factor. All right, we're still using the same function, but where do we get these T and R? We're simply updating them by looking at one step ahead in the future. Okay, fully exploited connections, blah, blah, blah. But in this equation, we see that we are using T and R. Where do we get this from? Because we say that we don't have that. The actual question is, how do we update our V without knowing T and R? Well, if we don't have the T and R, that means we will simply have to take samples. So we simply have to observe the environment and then get the evaluation and then averaging those, right? In order to find out the T and R. Okay, so how do we do that? Let's go over, let me just go over this. Now let's say that I have, I don't know where they're working, they're upstairs.
They're changing the nameplate.
Okay, all right, let's try to see if they stop. Otherwise, we'll just go and tell them to just wait for 15 minutes or so. All right, so what we do is, in order to get T and R, we take samples, multiple samples. That's what we have just talked about quite a for quite a few minutes today, right? We take one sample, right? Something like this. We took one sample, right? We knew the reward because right now we don't have the T. We have to find the T. So we know the reward, all right? And we may end up from one sample from state S, we can get into S1 prime, right? We get the average and then we get the value, right? We know down the value, and then we take another sample, then we take another sample, and we take multiple samples, and then we get the average. We calculate the average of it, right? So we simply take multiple samples and we calculate the average. But what is the problem with this approach in here? Now, suppose that, at one point in time, I'm in state S, and I might land in S1 prime. But in order to get the T, I have to average over all those samples, right? Like, in order to get the average between S1 and Sn prime, I have to get the average, but I have to know what happened. If I took a step from S, to S1 prime, then I also have to know the S2 prime, S3 prime, et cetera, et cetera. Now, in real world, I took one sample, one step forward, and I got into S1 prime. How do I know that? What happens if I go to S2 prime? Meaning I have to go one step back in the past. Can I do that? In real world, we can't. So in this way, all what we can do is, as we move along, we only get the average just from S1. It's going to be a really bad average, right? At every step, I'm only including the newly, taken step or the newly arrived state. So that's not going to be a good average that you're going to use for sample-based policy evaluation. So we have to fix that. How can we fix that? Well, we use temporal difference learning. Instead of looking at, taking the samples and going into the future by looking one step ahead, by looking into the future and updating the values of the future states. Why don't we update the values of the state that we just left, right? So I took a step, I went, moved one step forward. I actually landed in one state, and then I just update the value that I just left because I knew where I came from. So I just update my past and I just move forward. So that's called the temporal difference learning. Then that's called basically state, action, reward, and next state, and then next action possible to take. So that's the SARSA. So temporal difference learning, we will see how far we can get. So it can be one step ahead, it can be 2 steps ahead, it can be 3 steps ahead, it can be n steps ahead. N step SARSA. So SARSA algorithm is going to be, something very exciting that we will have to implement as part of the code, as part of a couple of applications that we will have to solve. Okay. Yes, runners. SARSA. SARSA. State, action, reward, state, action. Okay. So what we do is we just look at one step ahead. Okay. Policy is still fixed. We're still doing the evaluation, but we are only updating the values of the state that we just left instead of just the future states. All right. So what we do is we get this. All right. We get the reward and we get the value based on the existing policy of the next state. And we update the value of the state that we just left. Now you see, look at this equation. We took a sample, right? We got the reward of getting into the next state, right? We looked at the value, basically, once we get into the new state, we get that value, and we simply take that sample and we do the exponential average. That's called the exponential average by using alpha. Alpha is a learning rate. So you see here, this is what we know already. This is the state that we just left. So all what we do is we update our current value based on the sample that we have just taken. We usually keep alpha to a really low number, like 0.1. So alpha is between 0 and 1. If we put alpha as 1, then that means we are completely relying on new sample. And we are not relying on any of the value that was learned from previous, from previous samples, from the previous occasions when we were in that state. So we simply, put probably around like 0.1, something like that. And we value quite a lot, or we rely quite a lot on the existing value. And we just update it a little bit, just like 0.1 plus 0.1 based on the new sample that we have. And we learn slowly. Nathan.
So a high alpha would be sensitive. Alpha that's too low, be too slow.
Right. Yes, correct. All right. So we get that. So to write it more, in a more organized form, you just have V pi of S plus, alpha, learning rate, sample minus current value. That is it. If you, expand this equation, it's just this. So that's actually very similar to this slow learning rate of, how many of you have studied a machine learning course? Did you guys study gradient descent? Gradient descent, neural networks, how the neural networks are trained? Oh, really? Okay, so there's this very famous, gradient descent learning, algorithm that actually works on basically this is the error rate. How much error do you get when you get into a new state? How different you are from the previous known value that you had. You're getting a new sample, right? Now, this might be slightly different from what you already have. So you get the difference, you multiply it with alpha, you add it to the current value. So you slightly update your value based on the current sample. And if you take a lot of samples, your value will converge at one state. But remember, in temporal difference learning, we're updating the value of the state that we just left in, not the value of the state that we are getting into. Sounds good? We're going to use this formula quite a lot in the code on Wednesday and next week too. So please remember this. So example, temporal difference learning, something like this. Suppose that the idea is similar, but the algorithm is gradient descent algorithm is actually quite different. We will cover that in week 13 when we will look at neural networks. Okay, how to solve problems, several natural language processing problems using neural networks. We'll talk about that. Okay, so suppose that we have alpha 5 instead of 0.1 in here. All right, and gamma is 1. How do we do that? What we do is we simply update the value of the state that we just left in. Suppose that we had this situation, and then this one is our final, bigger reward that we have, because from here, the helicopter can come and lift us and we get the best reward, right? All right, okay. We observe the transition, right? From B, we took an action east and we went to C and we got the immediate reward of -2. All right, great. We get into the next state, look at the red dot, okay? Into the next state, and we simply apply this formula, right? Now you see here, so initially the value, this value from B was 0, right? So this entire term becomes 0, right? This entire term becomes 0. So this is 0.5, alpha is 0.5. We got the reward basically of -2 by taking an action from B to C, right? East from B to C here. We got the immediate reward plus -2 plus gamma 0.5. And what was the value of the next state? 0, right? So this is 0.5 times, what is it, -2? And we get the value of -1. We simply updated the value of the state that we just left. And the next time we took from C to D and we simply calculate the values and we update the value of the state that we just left. So if you plug in the formulas again, in here, plug in the values in this formula, you'll get the value of 3. So temporal difference is actually looking at going one step ahead and updating the value of the previous state that you just left. Okay. But there's a problem with temporal difference learning too. We're learning state values. How do we know that what is the best action to take? Right? Because we're going to simply be required to take the best action possible and update the possible the policy based on the best actions that we can take, right? So we will still have to use basically the maximum. We're going to still, we still don't know the T and R. We learn, one step forward, but we really don't know anything about the actions yet. So remember, we talked about the state and action value functions, and we were using the max function, right? So we have to calculate, or we have to compute the best actions or the maximum values. Well, you simply do the same thing. What you do is you get the Q values, all right? At every single time you basically take an action from a certain state, you note them down, the Q values, and from the samples that you have taken, you get the maximum from those samples. Okay? So that basically becomes an active reinforcement learning, optimal policies. So let me try to see if I can skip a slide or two to get the Q value iteration instead of the value iteration. Let me try to see. So the simple difference between the state value function, where we had vk plus 1, right, and s, that was the v pi of s, and that was 1 minus alpha. What was that? Plus alpha sample, right? And then we have expanded that formula. But in Q values, for the next Q, we're going to use T and R, but we'll come to that part in just a few moments. But we really can't use the V in here, pi of S. We can't. We actually have to use, we will have to use the Q values instead of the V state values in here, because we're learning for the Q values. Now you see, what we do is we update the next Q value based on the current Q value that we have, QK. and we get the max. So we expand. Let me just go over this in a more detail. So learn Q values as you go. It's just very similar to what we did with the state value functions. Okay, so with the Q values, every single time you take a certain action that you're in a certain state, only that Q value is going to be affected because we're using the max function. As soon as we use the max function, we're not going to be affecting any of the values. Suppose that in this state, if you were going to this square, only this value will be changed based on this Q value that we have, but because of using the max function. Okay, so let me get to that part. As I said, we really still don't know the T and R in Q learning and the value function. All what we have to do is we update our Q value based on what we currently have and what the next sample that we have. Very similar to what we just did with the state value function. Remember, like the sample, and here we have the value, right? V pi of s. Here, now we have to do Q, S, and A. The Q value, the best action that we have to take. And it's going to be very similar to what we did with the state value function, something like this. So you see, we take an action. Okay, let me just stop and explain what's the difference between exploration versus the exploitation. Okay, so what happens is that if you continuously or randomly explore the environment, then your learning can take really, really long, right? So every single time you're in an environment, you basically are tossing a coin or you're rolling a dice, right? That's the exploration. How long or how much exploration do you have to do? Every single time you get to a state, and then you're going to say, should I just choose a random action, or should I just look back at the memory and see if I took a right from this state, what happened? What happened in the past, right? Should I take advantage? Should I exploit that situation, or should I still just stay randomly? If you are always taking a random action, that's a very, very high exploration. And that can lead you to really, really long learning time because you're not exploiting any situation, any of the previous knowledge that you have. So the idea is for the agent that you slowly have to become, you slowly have to exploit the situations. You take more and more and more samples, and then you look at the knowledge that you have learned or that you have built from the past, and then you exploit that and see, no, I got into this state in the past, 9 out of 10 times, I basically fell down when I went into this state and this, at this certain step in the game, when I was in this situation, I fell down, I'm not going to take that action. So you exploit. How do you let your program or agent be, exploit the situation and not explore, always explore? Well, you simply use just an idea that's called epsilon, and it's called epsilon greedy function, by the way. Epsilon greedy, that makes you exploit the situation. How do you do that? Now you see, every single time, suppose that you're in this grade, right? Every single time, you still draw a random number. Basically, you roll a dice. That's a random number, right? Draw a random number. If your random number is less than epsilon, is less than an epsilon value, then choose a random action. Otherwise, if your random number is greater than the epsilon, then choose the best action. Then use the maximum function, right? Something like this. Random number, if it is greater than the epsilon, then choose random action. If it is less than the epsilon, then choose a random action. If it is greater than the epsilon, then choose a best action. And how can we over time become more, smart in order to exploit the situation? Well, what you do is, after several iterations, after several episodes, start getting the epsilon value, start decrementing in it, right? Like you start with 1, epsilon value 1, right? Then you're completely exploring, completely random. And over time, just start decrementing like 0.01 from it. And after several simulations or episodes, this will eventually become 0. And then you're always going to be exploited. Okay, so you're always going to exploit the situation. we will program that, by the way. We will code that in our problem that we're going to solve on Wednesday. Okay. And then you will see all these equations implemented in a really, really simple algorithm about, I think, 50 lines of code, 50 to 70 lines of code. And then you'll be able to solve a real world problem using reinforcement learning. But let me just show you the, Atari game. Has anyone played Atari game? This thing, right? So basically the idea is to eat all this, all these dots that we have. So what we did was this, DeepMind. How many of you have have heard about DeepMind? DeepMind. DeepMind basically is a company that is acquired by Google. It's a British company. And the guy from, he was the co-founder, I think, of DeepMind. And he did his PhD from Toronto, but he's from London. His name is David Silver. And he basically teaches reinforcement learning at UCL as an entire course. Great guy. He does a very, very good explanation. And the DeepMind was the one that designed the game of Go that beat the world champion. Remember week number 1. He was the mastermind behind it. He's also one of the masterminds behind this game that they developed. All what they did was they had an image, basically pixel values, right? Based on the image, they learned the cue values. So like where exactly to put the base, right? For the ball to bounce and then eat the, darts or, as quick as possible. So they used that, pixelated information, image like pixels, and then they trained a trained a neural network, deep cue neural network, to learn the cue values. What is the best action to take when there is a certain situation in the game? So, initially what you do is the beauty of that game was that, we'll play the Atari game by itself, all right? And after that, the agent is given sensory input. What you see in the screen is it was ordered to maximize the score on the screen. Okay, so the more dots the program eats, the higher the score is. So the idea was basically try to hit the ball back, but it is yet too clumsy. Initially, you see, like there might be several situations where it will lose. You see, there are episodes where it is losing. So the score, the idea was to increase the score that was being implemented there. So after several iterations, they learned the cue values by basically putting the base into a certain, location so that to eat more darts, and increase the score. After several iterations, it actually becomes better and better and better because your cue values are being learned, the best action. That's why I said, instead of just learning the S state values, you also learn the cue values. So get the best action. But the magic happens here. This is where the magic happens. It realizes that the digging a tunnel from a side and going at the top and eating all the dots, that's the best possible actually. Now you see, at a certain point, it will actually start digging a tunnel from a side, and then the dot will basically go up, and then it will eat most of the dots. Look at that. And basically it updates the score. We will also design Atari game. This thing in our class, hopefully Monday next week. We'll write the code for Atari by basically using deep learning, and we'll learn the cue values to find out how good our program is compared to this. Okay, using reinforcement learning. Yes. Are we what? Sorry. Python. Yes. Yes. I will do all the programming in here on my computer. You'll just watch. But if you are interested enough, you can come up and start typing if you want. Okay, start writing the code if you really want. That will be totally up to you.